For test 2. I know that normally these come out sooner. I actually had already made one, but when I made it, I was a little distracted, having like a little bit of an off day, so I felt like it would be better for me to go ahead and remake it so that I could spend the time I needed to thoroughly explain everything. So this first question is asking the substituent group 1,1-dimethylethyl has the alternative name of what? So when we talk about substituent names, if you have methane, that is a parent chain all by itself of just one carbon. But if we change it from methane to methyl, if we take away the ane and make ill, then we know that's a substituent. And a lot of times the parent chain will be designated as wiggles, and then you just have that carbon off of it. So this wiggle means any parent chain possible. So this is asking, what if you had a substituent that you would name 1,1-dimethylethyl? So if we had a parent chain, and off of that parent chain is an ethyl group, so I'll start by just that. That's the parent chain of the substituent. So substituents, if they are more complex than just one or two carbons, you have to name their parent chain as well. So in this case, this parent chain is ethane. But because it's a substituent, we don't call it ethane, we call it ethyl. And numbering for these parent chains start closest to the actual parent chain. So if you're doing a parent chain of a substituent, the number starts at the first branch off from the primary parent chain. So this is the ethyl group, and then it has to have two methyl groups because we have 1,1-dimethyl, and they need to both be at position 1. So that looks something like this. And so once you draw that out, then you should start to recognize this group that also has the common name tert-butyl, a carbon with 3 carbons around it, making a total of 4 carbons. And that is one of the common names that you had to learn that we'll use a lot throughout the rest of organic chemistry. Okay, the next question, what is the relationship between the following two molecules? So the first thing I'm going to check to see is, are these isomers or not isomers? So do they have the same number of atoms, carbon, hydrogens, and bromines in this case? So we have 1 carbon, 2 carbon, 3 carbons, 1 carbon, 2 carbon, 3 carbons. Oh, actually I counted that wrong. Let me erase that. There's 4 carbons actually each on each of these. So I'll highlight the parent chain first, here, and here. So for both of these, I see 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. So for each of these, we have 4 carbons. They're both butane. So 4 carbons on each side. We have 1 bromine on each one. So the moment of truth is how many hydrogens are there. There's 3 hydrogens here, 1 right here. So 4, 5, 6, because there's 2 hydrogens here, and 3 more here, so 9. So 3 here, 4, 5, 6, 7, 8, 9 here as well. Okay, so these are isomers. So we definitely know they're not isomers because they're totally different molecules. I guess I should say they're isomers or they're the same because they have the same number of carbons, hydrogens, and bromines. So now we determine, are they constitutional isomers or stereoisomers? So when you're trying to tell they have the same number of carbons and hydrogens, whatever, they could be isomers, constitutional, which means they're attached completely differently, or stereoisomers. And a quick way to tell are these constitutional isomers or stereoisomers is if they have the same parent name and you just specify like RS or cis trans, then they're usually constitutional isomers. If their name is different, then they're usually, they're stereoisomers if they have the same parent name. If they have different parent names, then they are constitutional isomers. So like an example of this is, this has 1, 2, 3, 4, 5 carbons, and it's named pentane. And this has 5 carbons, but it would be named 2,2-dimethyl propane. So even though they have the same number of carbons and hydrogens, they have different parent names, which means they are probably constitutional isomers. So in this case, that's kind of where I like to start, is I'm like, are these both attached in the same way? They are both butane as the parent chain. And they both have one substituent of bromine, and for both of them, that bromine is on carbon 2. So both of these are 2-bromobutane. So these are definitely not constitutional isomers either. So we've narrowed it down to diastereomers, enantiomers, or just being the same molecule. Well, diastereomers have to be cis-trans, or they have to have 2 chiral centers. So there's no alkene, so it can't be cis-trans, and I only see 1 chiral center right here. Everywhere else has at least 2 hydrogens attached on both of these. So they're not diastereomers either. So they're either enantiomers or they're not isomers. They're the same molecule. I'm going to erase the work I've done so far so that it's easier for me to assign R and S configuration. And that will tell us if they're enantiomers, are they mirror images or not. So one way that you can do it is by assigning the chirality, right? That's one option. Another option is if you're good at rotating molecules in your mind, you could see, do they look like mirror images? So when I'm looking at this, I'm seeing these bromines are lined up, but these two are not lined up. So I'm going to try to get the bromines to be just on, so I don't think they're the same molecule, because if the bromines lined up but the other two aren't, that makes me think that they're probably enantiomers. So that's my first clue. But just to make sure, I'm going to rotate these 3. I'm going to leave the bottom one the same because it's CH3 on both of these. And I'm going to redraw this molecule. I'll do it in a different color so you can kind of see. I didn't rotate the hydrogen or the methyl group on bottom, but I'm going to make this bromine come over here. So I moved the bromine from the left to the right. I'm going to move the hydrogen from the right to point up, and then I'm going to move this ethyl group over here. And if I draw it like that, you can see that the ethyl groups are facing each other, the bromines are on opposite side, and the hydrogen and the methyl are in the same place. So to me, this does look like a mirror image. But if you're still not convinced, the next thing we can do is assign R and S configuration. And what's nice is we already have the hydrogen pointed away from us, so that makes it a little bit easier. So obviously the bromine is priority 1. Then the hydrogen is always priority 4. If there's a hydrogen, it's going to be priority 4 usually. If there's 2 hydrogens, it's not a chiral center. Then between these two, they both have carbons attached to it. The ethyl has another carbon, so that gives it the edge over the methyl, which only has 3 hydrogens. So that would be priority 2, and this would be priority 3. So we connect these 3 together, and we get our configuration. Now this, I'm going to assign the priorities are the same. Oh, I'm going to do it on what we redrew. 1, 2, 3. They're going the opposite direction, so these are S. So these are definitely enantiomers, and there's a lot of different ways you can solve it. If whatever is easier for you to visualize, you kind of have to figure that out and work through it. That's just my process. Okay, the next question, what is the correct name for the following compound? So you can find the parent chain. This looks like the parent chain to me, although this one over here is a little bit longer, so I'm going to see what happens if I highlight this, how many carbons are there. So on the green one, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. On the orange one, we have 1, 2, 3, 4, 5, 6, 7. Okay, so the orange one is not looking like a viable option. I think green is the parent chain. Now the next thing you can do is number both directions to see which one gives you your lower substituents, because the first step, maybe I should write that out for you. I do 3 steps. Step 1 is find the parent chain, which we did. Step 2 is find the substituents and number them. Because oftentimes you can't number the parent chain until you've found the substituents. So I numbered it from right to left, but I usually will also number it the other direction just to make sure I have both options. Then I circle the substituents. So here's one substituent and here are the others. I don't see any more than that. So now I'll write these out and I'll give them both numbering systems. So we have, I'll write it in this color. We have dimethyl, and they're on the same carbon, so we'll need 2 locants, or 2 numbers of where they are, and then we have ethyl. And the next thing is we're going to see what we number them. So if we go with the orange numbering, it'd be 5-ethyl and 6,6-dimethyl. If we go with the navy numbering, it's 3,3-dimethyl and 4-ethyl. So these are the lower numbers, so that's what we go with. Now, if there was an alcohol or a different higher priority group, we would have to give that the priority in naming. But if all of these substituents are the same priority, then we go with getting the lowest overall number. So, and then you also have to be sure to write both your locants if you have dimethyl. So you have to specify even if they're on the same one, so there's no ambiguity, so there's no question. So then the last step I do is I combine it all in alphabetical order. And to do that, I would look at, you don't look at the die, you don't look at the number of them, you only look at the first letter. So combining this all, we would have our ethyl first. So it would be 4-ethyl, 3,3-dimethyl, and then the parent chain is 8, so octane. So that's usually what I do. Now, if you're on a multiple choice question and you're trying to eliminate wrong answers, the first thing is we're pretty sure that octane is the parent chain. Usually if there's one longer than that, like nonane, I'll double check to make sure there's not a nonane anywhere present. I don't see one. So we have two options now. And just looking at both of these, if you know the rule about alphabetical combining, you can't have your methyl before your ethyl, so that's wrong too. So the only options left are these two. So comparing what you got to this, it looks the same, and so this is the right answer. But that's kind of the process I use to eliminate answers that are wrong. Okay, next question. Which of these structures below would be considered staggered anti? So there's eclipsed in a Newman projection. Looks like this, where the two carbons are sitting sort of on top of each other. Whereas anti is the, or I guess staggered. There's a eclipsed versus staggered. So eclipsed is where you have them like this, and staggered is where all the carbons are opposite each other, so you can see each one. So based on just that, I'm eliminating option 2. And then anti will have the biggest groups opposite one another. So usually if there's any ambiguity, I'll tell you which two are the biggest groups, but in this case, when we're looking at all the groups, it's only hydrogens or carbons, so obviously the carbons are the bigger groups. Now, when the two carbons are next to each other, that's considered gauche. So this is staggered, but it's staggered gauche. And the same thing is true for this one and this one. The two biggest groups are next to each other. So that only leaves 3 for anti, staggered anti, and these two big groups are completely opposite each other. So answer choice C is right. Okay, next question. How many chiral centers are in the molecule below? So I actually adjusted this question. There's no 6 or 7. That is kind of a hint to you, is that I want you, it was easy to find 6 or 7, I thought, chiral centers. Easy is relative because all these questions are hard. But whenever I went through it, I very quickly identified 6 and 7 chiral centers, but I got stuck on finding the 8th one and it tripped me up. So to make this question a little bit easier for you, I took away those two so that you could be sure to find it. So either you could find most of them and figure out, oh, there's probably an 8th one, or if you're not getting to 6 or 7, then then you need to practice a little bit on finding your chiral centers. But that was kind of how I tried to make this question a little bit easier for you. So when I'm looking for chiral centers, I am knowing at first any carbon chain like this has 3 hydrogens or 2 hydrogens, right? So any long carbon chain, like when I'm seeing these carbon chains right here, I'm immediately taking them out of my mind because I know they have several hydrogens there. Same thing with this one. There's a hydrogen on that. So all these things that I'm highlighting in green, these are ones that I'm immediately like, oh, they don't have what I'm looking for. This must have 2 hydrogens. 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 Any carbon angle that doesn't have anything bonded to it must have 2 hydrogens. So I immediately get rid of any of those sp2, sp3 hydrogens or carbons with no substituents on them. And then I'll check what's left. And one of my students said she watched a video that said you look for the Mercedes-Benz. Oh, here, I'll do it. The Mercedes-Benz symbol. So the Mercedes symbol looks like that. So she looks for a Mercedes. And if the three things attached to the Mercedes are all different, then that's a chiral center. Now, I'll say if the three things, the total of them are all different, because this is a carbon, and carbon, but you have to keep going down the line. This is a CH3, this isn't bonded to anything else, and this is an oxygen. So all three of those are different. So that's one chiral center. Here's another chiral center. sp2 hybridized can never be, so I'll eliminate those as well. sp2 hybridized can't be chiral centers because you have to have four things attached, and if you have a double bond like that, you can only ever have three things attached, 3 electron domains. So I'm just circling all these. This one right here that I just drew, that one's a little bit trickier to find, but if you go through, you will see that it has 3 different ones attached to it. I'm going a little bit more quickly than normal, but because hopefully you've seen me work a few questions like this already. So then I'm counting 1, 2, 3, 4, 5, 6, 7, 8 chiral centers, and so that's my answer. Oh, here's another sp2 hybrid that I would have eliminated, and heteroatoms aren't usually going to be chiral centers at this stage, so you can eliminate those. So we're just looking for carbons that don't have multiple hydrogens attached to them, basically. Okay, next question. What is the name for the following molecule? So again, my first step is find the parent chain. And the parent chain I'm looking for, in this case, I notice that there's an alcohol, so it has to include the alcohol attached to it. It doesn't have to start with the alcohol, but the alcohol does have to be included. So I'm going to start right here with the alcohol included. And I can either go to the right, which has several carbons, to the left, which only has 2 carbons, or to the right, which has a lot more. So I'm going to go to the right, and that is the longest chain I can find. So we have 1, 2, 3, 4, 5, 6. So this parent chain is hexane. So if you just knew that one rule that the alcohol has to be included, then you could get rid of the heptene and this heptene here as well. Now the next thing I'm noticing is this one right here doesn't have the locant before each letter, or each substituent, so that makes me suspicious that this is probably not right, but I find it easier to solve the question first before eliminating things like that, so I'll talk about that more a little bit at the end. But so we know that hexane is our parent chain, and then I'm gonna circle my substituents. Here's one and here's the other. And you could number it technically starting this way, but you need to start with the higher priority, and alcohol is the highest priority, so I'm gonna leave my numbering the way it is. I only have 2 substituents. One is an alcohol, and so I'm going to say it's 1-OL because this is a suffix. So the alcohol at position 1, we had alcohol as a suffix, so 1-OL. And then the second one is an isopropyl, and that would be 2-isopropyl. You could also call that 2-methylethyl. And then, I guess technically this is a substituent as well. Then your alkene is 4-ene because that's also a suffix. So for me, it's easier to write them out with the name that they will go on. But if you like to write 1 alcohol or 1 double bond, you can do that. 4 double bond, you can do that as well. Okay, so now when I'm combining this all, I'm going to say this is 2-isopropyl. It's in alphabetical order, but there's only 1 at the beginning. 2-isopropyl hex. And normally what I do is right before the substituent, I write the number. So hex 4-ene. And you might be thinking, well, why did you put the double bond before the alcohol? Is it because it's also alphabetical? No, it's actually because it's the higher priority. So when you get to the end, you put the higher priority first and the lower priority first, and the highest priority goes at the very end of the chain. So 4-ene, and then I drop the E because that's how we do our suffix for alcohol. Normally if it was hexane, we would get rid of that and call it hexanol. So 4 ene and then 1 all is the overall answer. Now, this one is numbered incorrect, so I could eliminate it based on that. But if that wasn't enough for you, this 2,6-hexenol is too ambiguous. So if they were trying to write it to where it was the 2-hex, they would need to write 2-hexene and then 6 all. But they didn't do that. They put 2,6-hexenol, and that makes it ambiguous to where we don't know if the 2 is for the ene or the all, because you would put the lower number first. So that doesn't follow the rules. So this is wrong in 2 different ways. And I did forget to put my trans here. Trans goes before all of it because there's an alkene. So answer choice B is correct. Okay, this next question, I actually adjusted this because it was much harder. And there was like several answers that were kind of tricky that I wanted to make it a little bit more straightforward for you. I'm never trying to trick you. I'm just trying to check your knowledge. So on this one, which of the molecules below is a diastereomer of the molecule given? So when I'm looking at this molecule and I'm thinking diastereomer, diastereomers are usually either cis-trans or if you have 2 chiral centers. We don't have alkenes that would be cis-trans. We just have this whole ring. So I'm looking at these 2 chiral centers right here, and I'm guessing we're only going to change one of them. If we changed both, then changing both of them, it would become an enantiomer. But if we only change one, then that is a diastereomer, because it's not a mirror image, but it's not the same molecule. It's a different stereoisomer. Okay. So now with all that in mind, I'm looking at this first one, and there's a double bond here. So that can't be right, because if we add a double bond, it's no longer the same molecule. So these 2 are our only options. When I'm looking at this, it looks like our OH has been changed and our NH2 has been changed on this one. So this is the enantiomer. So I'm going to get rid of that one. And now this one, answer 2, the alcohol has obviously changed, but I can't tell for sure if the other one has changed as well. So I'm going to check myself that way. And for me, it's easier to draw in the hydrogen as well, because there is an implied hydrogen. It's implied here also. So I'm going to try to rotate this, and I'm going to rotate it forward so that I can get the NH2 back to the wedge where it was in the first picture to see if it's the same or not. So if I rotated that whole thing, the alcohol hasn't changed, but now I've moved the CH3 up to be in the plane of the page. I've moved the NH2 to be on the wedge moving forward, and that means that the hydrogen went back to the dash. And so it looks like we have inverted this top chiral center, but not the bottom one. And so we've only changed one, so answer choice 2 is your answer. That's one way you can work it. That's how I visualize it, is by rotating the molecules. Alternatively, you can assign the, if you need to look at that, you can rewind the video or whatever, but an alternative option is to assign the chiral center. So if I'm looking here, here's one chiral center, and then here's the other one. So I'm going to assign the priorities. Obviously, oxygen is first priority, and then we have 2 carbons. This carbon is bonded to 3 other carbons, I guess. 1, 2, 3 carbons, whereas this one is bonded to a carbon, a hydrogen, and a nitrogen. The nitrogen actually should outweigh the carbons on the other one. That's a little bit tricky, so I won't usually give you a question that's asking that specific thing on the test. And if you're ever not sure, as long as you assign your priority the same both times, even if it's not the right answer, if you're comparing between 2, like you are in this case, just be consistent and it'll get you to whether it's the enantiomer or not in this case. I wouldn't give you a question like this and just tell you to tell me what the chiral center was. Okay, so in this case, I'm going to say this would be carbon, this would be second priority, and then this would be third priority. The hydrogen's already pointing away from us, so that's nice. So this is our configuration. Now looking at the I'm going to erase just this circle. Looking at the nitrogen, this carbon right here, we have a carbon, and a nitrogen. So the nitrogen is the highest priority. And then we have our 2 carbons, and between these, this carbon is bonded to other things while this one's not. So 1, 2, 3. So this is also our configuration. I'm going to erase that. Okay, so now I'm going to do the same thing down here. I already know that my OH is pointed towards me and everything else is the same. So immediately I'm like, oh, well, this is S configuration down here. Just because my only things that have traded is the implied hydrogen back here is now on the wedge. So just swapping out 2 will switch, just changing 2 groups and nothing else, leaving everything else the same, changes the chiral center. But what I am going to do on the second one is assign my priorities the same way, but I'm going to know that the hydrogen, the implied hydrogen, is pointing towards us. So whatever our S configuration, absolute configuration I get, it's going to be the exact opposite. So we'll just have to switch it. So the nitrogen is position 1, this is 2, and this is 3. So if I connect all these, it is S configuration, but because the hydrogen is pointing toward us, we can go ahead and flip it and say it's R. So we went from RR configuration in the first, at first, to SR in the second. So I think it's faster personally to rotate the molecules, but everyone approaches questions differently. So that's why I try to give an explanation on how I worked it out for each person. Okay, next question. The most stable conformation of the 3-bromo-2-methylpentane viewed through this bond, C2C3. You're supposed to choose which one. Oh, which I didn't say that, but the most stable conformation viewed through the C2C3 should say is which one. So there's might be a little bit of confusion on that, but the way I would approach this, and you can reach out if you were confused on that, and explain how that impacted your answer, not knowing what you're supposed to do. The way I would approach this first, if you know nothing else, hopefully you know that staggered is more stable than eclipsed. So I'm going to eliminate this answer because it's eclipsed. And so it is likely not the most stable conformation. The next thing is we want the 2 biggest groups to be anti. But we can worry about that later. First, we're going to eliminate any that aren't the right molecule at all. So if we have on carbon 3, we have a bromo, 3-bromo. Carbon 3 is in the back. So looking at my Newman projection, the carbon in the front is the one that sort of does the Y, and the one in the back is circular. So the one in the back needs to have a bromo on it because 3-bromo is in the back. So that's what I'm looking for. So I'm going to go through and eliminate any of these that don't have the bromo on the back carbon. So this has the bromo on the back carbon, so that's good. This has the bromo on the front carbon. See how it's on the Y shape? So that's wrong. This also has the bromo on the front carbon, and it's in the Y shape, so that's wrong. This has the bromo in the back. So those 2 are all that it's left, basically. We just have 2 options. So the next thing I'm going to do is look at the other substituents. So we should have 2, I'll do it in a different color, 2-methylpentane. I guess we don't need the pentane, 2-methyl. So on carbon 2, which is in the front, we need to have a methyl group. So I'm going to look for that. So carbon 2, we should have a methyl. And it doesn't matter if there's multiple. We just at least need 1. Carbon 2, we have a methyl. Okay, so both of these to me seem close. The next thing I'm going to count is my number of carbons. So I'll just start with one of the methyls would be carbon 1. And we know that one of the methyls will be carbon 1 because it's pentane, and this is carbon 2 is the Y in the middle. Carbon 3 is the one on the outside, so we need carbon 4 and 1 other carbon. So this one does not have the full number of carbons that we need, actually. This only has, we need pentane, so we need 5 carbons and a methyl. We only have 1, 2, 3, 4 carbons and a methyl. On this other one down here, we have 1, 2, 3, 4, 5 carbons and a methyl. So just by being able to count the number of carbons in pentane and by being able to tell which of these has all the right substituents on it, then we don't even have to worry about which one's the most stable because there's only one that has everything that we need in this molecule. So if that is a hard way for you to think about it, another way you can think about it is you can just draw out this structure. So this is pentane. We have a bromo and we have a methyl. And it doesn't really matter. It doesn't give us R or S configuration. You don't technically know that yet when you learn about Newman projections, right? So one's going to be a methyl, one's going to be a hydrogen. So I'm just going to draw this out if I was looking at it from here. So the CH3 would be on my right, the hydrogen would be on my left, and this would go down. And then in the back, we have an ethyl pointing up, a bromine, and another hydrogen. So if you just draw that out and look for these structures, that would also help you. So you're looking for a CH2, CH3 on the back carbon. If that's, once you have this drawn out, I'm going to erase what I already did so that I can approach it from this. If this makes more sense to you, once you draw this out, you can compare just on the front, I need 2 methyls and a hydrogen. So on the front, I need 2 methyls and a hydrogen. On the front, I need 2 methyls and a hydrogen. I don't have that on this one. On the front, I need 2 methyls. Don't have that. On the front, I need 2 methyls. On the front, I need 2 methyls. Okay, so that gets you down to just these two. And then on the back, I need an ethyl and a bromine. And on the back, I have a CH3 and a bromine, so that's wrong. And on the back, I have an ethyl and a bromine, so that's right. You can double check the rest of them, but that should be the right answer at that point. Okay, which of the following is the correct structure for R2 pentanol? You can also write this R2 pentan, or sorry, R pentan 2-ol, whichever one of those you like better. I like putting it directly in front of the substituent every time because it is a little bit clearer. But again, I'm going to eliminate answers based on what I know. Pentanol looks like this, 1, 2, 3, 4, 5. And so it can't be the first one. That's a cyclo. And then we only have one substituent. It's an alcohol on position 2. So this one's wrong too. So it's got to be one of these two. So whenever I'm trying to assign priority, I usually will pick the one that has the hydrogen already pointing backwards because that's easier for me to do. So this is laziness, but this one you don't have to rotate anything. The hydrogen's already pointed back. So this is going to be priority 1 for the alcohol. Both of these are carbons, but this one is attached to another carbon while this one is attached to 3 hydrogens. So the one on the left is 2 and this is priority 3. So I'm going to connect these 1, 2, 3. This is going counterclockwise, so this is S, and we're looking for R, so that's not right. This, to me, looks like the mirror image of that, but you can work it out if you want. The hydrogen's pointing towards you, so whatever you're gonna get is going to be the exact opposite of what you want. So 1, 2, and 3. And so that's S, but the hydrogen's pointing towards us, so in reality, that's the mirror image, and we get R. So answer choice 3 is correct. If the thing where it's like one of them pointing towards you doesn't make sense, you can also rotate this whole molecule. So if you were to flip this whole thing, it would look like this with the alcohol like that. So however makes sense to you, that's how I process it, is thinking about the hydrogen being pointed towards me or away from me, but either one of those is correct. Okay, this next question, which of the following represents the Fischer projection of the compound shown? So Fischer projections are basically a projection where you're assuming that anything pointed up is going away from you and anything off to the side is coming towards you. So this is kind of what it looks like, but it's just easier to draw it like this. And these are used a lot in biochemistry. So if you are going to have to take biochemistry, you need to know Fischer projections, and especially for amino acids. Amino acids are often depicted this way. And so if you ever need to be able to assign the chirality of amino acids, you're going to need to have these Fischer projections in your mind. So for me, what's easiest to do for Fischer projections is to rotate the molecule. I'm going to draw in the hydrogens here. To rotate the molecule to where it looks kind of like this. And if you need a more detailed overview of this, the exam 4 and 5 review I did that was in the exam prep module is going to be really helpful. And so that way you can imagine yourself as a person. I always imagine myself as a person floating above, like right here looking down. And then these two things are coming up towards me, whereas this is going away from me from that angle. So it's hard. This is really hard to do because you're trying to visualize something really from multiple angles. And this is why I allow your modeling kit on the exam, is because you can use your modeling kit to visualize this. Now the one on this side, we have the thing in the plane of the page pointing up. And so we need to rotate that to be pointing down, which means these will get rotated. And when they get rotated, they're going to switch from being on a wedge and a dash to being on a dash. So like something that helps me visualize this is if you hold your finger and your thumb in the shape of an L, and now take that and point it down. So your thumb is pointing down and towards you, and your finger is pointing down and away from you. If you rotate that so that you rotate your wrist, so now they're both pointing up. Your thumb is now pointed away from you, and your pointer finger is now pointed towards you. So essentially, your thumb went from being pointed down on a wedge to being pointed up on a dash. And the same thing happens here. So your alcohol, which was on the dash, so pointed away from you, pointed down like your index finger, if you rotate that, is now going to be pointed towards you. And then the hydrogen is going to be pointed away from you. So on this question, you're going to look for your alcohols to be on opposite sides. And they also need to be, on their each respective carbon. So this first one has 2 alcohols on the same carbon, so that can't be right. Same thing for the second one. So you can at least narrow it down to these 3. So you get yourself from a 20% answer to getting it right to getting a 33% chance of getting it right. And both of these have the alcohol on the same side. And that was a hint for you to say like, oh, wait, these alcohols, there's something else on there that is wrong on this one. There's an alcohol on each respective side, but this one, question 3, has 3 alcohols on it. So you can immediately get this down to only 2. As long as you notice those. I hadn't even noticed that. So now looking at these 2, you would have had to know that it flips over. But as long as you knew that it flips from being a wedge to a dash when you rotate it, you would be able to get this to answer choice E. Or D, sorry. Okay, next question. Identify the cyclohexane chair conformation with 2 equatorial groups. So equatorial groups are the ones that go out, or equatorial, however you want to say it, at an angle looking like this. And so anything that's pointed straight up or down is axial. And they'll usually alternate what's pointing up or down. So I'm looking for anything that's pointed straight up, and I'm going to eliminate that answer, or straight down. Straight up, both of these are straight up. This doesn't have any pointed straight up, so this is a good answer choice. So for that, you just kind of had to know what equatorial versus axial was. Identify the absolute configuration of the chiral center in the molecule below. Okay, so this is our chiral center. It's bonded to a carbon, an oxygen, and another carbon. So the oxygen is definitely priority 1. Now between these 2, this is a little bit tricky because they're both of these carbons are bonded to 2 hydrogens and then an oxygen. So this carbon is actually the same. So you have to go to the next point of difference, which is the oxygens. One oxygen is bonded to a hydrogen and the other is bonded to another carbon. So this would be priority 2 and then this would be priority 3. The hydrogen's implied and pointing away from us. So 1, 2, 3. This is an S configuration. Which of the molecules below shows 2 methyl substituents in a cis configuration? Okay, so cis is either they're both up or they're both down. And so I like to draw, if we had all these methyl groups cis to one another, they would actually be alternating axial, equatorial, axial, equatorial, axial, equatorial. And I have a good video on this if you're not sure, but if I were to draw these same groups that I have on the left, axial, equatorial, you see how they're pointing up, axial, equatorial, axial, and equatorial. So we're looking for not necessarily multiple axial or multiple equatorial, we're just looking for two that are both pointing up. And so I'm looking at this right here, which has an axial pointed up and an axial pointed down, and I'm thinking that's not right. But if you're not sure, you can also circle, okay, we have these two. If they were both cis, one would have to be an axial and one would have to be an equatorial, but these are both axial, so that one is definitely wrong. Now for this one, we have an axial and an equatorial, but they're 3 carbons apart. So if this first one's our axial, and then we're looking at the other one, if it were also pointed up, it would also need to be an axial. So that one can't be right. Now, if we have our axial, carbon 2, 3, 4, we're looking at an axial, carbon 1, carbon 2, carbon 3, carbon 4. So one's an axial, one's an equatorial, and to me these do both look to be pointing upwards. They're not pointing down. So this is probably our right answer, but I'm just going to check in case it's more than one of these. We have axial at this position, and then, oh, let me change my pen color. We have an axial at this position, and then 1, 2, 3, an equatorial at this one. So if we had axial at position 1, 2, 3, we would need another axial, but it's equatorial, so that's not right. So I am going to stick with my answer of answer C. Some people can just, I'm going to erase all this work, but you can always pause the video. Some people can just look and see based on this, like which ones look like they're pointing up and which ones look like they're pointing down. So like these that I've highlighted all look like they're pointing up, and then these look like they're pointing down. So if you can see that, that's great, but if not, I couldn't at first, I have to do this. I used to have to do that mode. Okay, this reaction is the one that just gets rid of the double bond and replaces them with hydrogens. And so that would result in pentane. These didn't get rid of the double bond. You just need to know that one. These two didn't get rid of the double bond, so neither of those could be right, and pentane would be the right answer. Okay. What is the relationship between the following two molecules? So this kind of goes back all the way to what we started with, which is, are they, totally different molecules? Are they isomers? Are they the same molecules? So we have carbon, oxygen, and hydrogen. Let's just see how many of each of these we have. 4 carbons on this one. 4 carbons on that one. 1 oxygen on each of these. And how many hydrogens? We have 3, 4, 5, 6. I'm not going to draw them all in. 7, 8, 9. And then 1 on the alcohol. So that's 10. Now we have 3, 4, 5, 6, 7, 8, 9, 10. Okay. So these are definitely not totally different molecules. They could be, in theory, an enantiomer, diastereomer, constitutional, or not isomer. They could be the same molecule. But again, like I said before, I like to look at the parent chain and see like what would the parent chain be named here. And the parent chain on this one is definitely butane. So that's pretty straightforward to see. But then if you're looking at the parent chain on the other one, you haven't even learned how to name a molecule like this, but it's definitely not butane because they're only 2 carbons bonded together at once. So to me, our parent chains being different is a good clue that it's constitutional isomers. Okay, on the Fischer production below, please indicate where the appropriate substituents would go for this molecule. The lowest priority groups have been added in vertical positions to ensure consistency. Carbons 2 and 3 have been labeled for clarity. If you're not sure where to start, draw the Fischer projection yourself first. Sorry, I ran out of water right when I started this video, and it's getting harder to talk. Okay, so I'm going to start by not worrying about these, but I'm just going to start by drawing this. 3-chloro, 3-fluorobutanol. And I'm going to draw a CH3 here and a CH3 here, so that makes it very clear. I have carbon 1, 2, 3, and 4. That's how I'm going to draw it before I even look at the answer choices. And I know that carbon 3 has a chlorine and a fluorine. And I know that carbon 2 has an alcohol, and then it must have a hydrogen. So this is, I've now drawn 3-chloro, 3-fluoro-butane, 2-ol. Drew that. Great. Now I'm just going to assign R or S priority to see if I have drawn it already in S configuration or if I need to change something. So first I'm going to say what the priorities of these are, and I'll use purple for the top one. So this alcohol is obviously priority 1. Hydrogen's priority 4. It's pointing towards us, so that means we're going to have to flip this before we finalize it. We have 2 carbons, but one carbon has a lot of heteroatoms and the other just has hydrogen. So these are my final priorities. 1, 2, 3. So this is our configuration as written, but remember the hydrogen's pointed towards us, so it's actually S. So that's nice. That one's we already have S configuration. Now I'm going to do the next one. The highest priority is chlorine, then fluorine. And then between these two, there's 2 carbons, but this carbon has heteroatoms, so this is 3. And then carbon 4 is already pointed, or the lowest priority, the CH3 is already pointed away from us, so that's great. So 1, 2, 3, so this is to the left, so this is S configuration. So this is super handy for me. Just the random one that I picked already has SS configuration. So nailed it. How exciting. So I know when I'm looking at this, the bottom one, we have the fluorine on the right and the chlorine on the left. But then up above, my hydrogen, I put over here. So I'm going to have to rotate this to get the hydrogen pointed up. So if I were to rotate that, the alcohol would be on the left. Then the hydrogen would be pointed up here, and the CH3 would be on the right. So I just had to rotate that to get where I wanted it to be. So the left would be OH, the right would be CH3, and then for carbon 3, the left would be chlorine, and the right would be fluorine. Okay, next question. If you're trying to determine the absolute configuration, what priority would you assign to each area? So I know we've had a lot of absolute configuration questions already, so this seems like a little bit straightforward, but I'm trying to give points for the process in case some of those other ones were harder for you. So the first thing I'm looking at is I'm looking at this oxygen right here. Oxygen, where everything else is carbon or hydrogen, that purple to me is going to be priority number 1. And then the green would be priority 4. So now I just have to decide between blue and orange. Both of these are carbons, but of course this carbon has 3 hydrogens, where this only has 2 hydrogens and another carbon. So that gives it the edge, and then the last one would be, oh sorry, I put priority 3, but it's priority 2. And then the orange one would be priority 3. Okay, so blue is priority 2, purple is priority 1, green is priority 4, and orange is priority 3. Okay. Next question, name the molecules shown in the given Newman projection. Be sure to include stereochemistry where appropriate. So the first thing I do, just like any naming, is first I find the parent chain. So let's find the parent chain. And it's a little bit harder here, but I am instantly drawn to this long chain here that goes to my carbon 1. Now from here we have 2 options. We could either, or not carbon 1, but my carbon in the front carbon. We could go, this is 1, 2, 3, 4. Now we could either go 5 here to the carbon in the back, 6, or we could go 5, 6. So it seems to me like either of these is going to give us 6 carbons. So for me, kind of an easier way to draw this type of problem out is to, when it's even like this, it could go either way, is I actually will draw the Newman projection where between these 2 atoms. So if I'm going from Newman projection to the normal bond line, we'll say this is carbon 4 and this is carbon 5 based on the way that we drew it here in in our Newman projection. That doesn't mean that's what they'll stay in the final numbering, but I'm just going to draw it out, make it easier. So the front carbon has, carbon 4 has this isopropyl on it. And then we'll say pointed towards us is a hydrogen, and pointed away from us is this long chain with 3 carbons. So let me draw that better. 1, 2, 3. Is that too many? 1, 2, 3. Yeah, that's 4. So this is carbon 1, 2, 3. Okay. And then the back one has pointing up, we have 1 hydrogen and then another hydrogen, and then pointing down is a methyl. So that, for me, is easier to see. The next thing I'm going to do is try to count to see which is the parent chain. So we could go 1, 2, 3, 4. My iPad. 1, 2, 3, 4, 5. 1, 2, 3, 4. 5, 6, or 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So either of these could be the parent chain. And now we want to choose the one with the fewest substituents. Looks like, and the less complicated substituents, I guess. So this has the ethyl, which is just 1, and that's a little bit easier, as we have ethyl and methyl on this one. Or if we do the parent chain, I'll do it in this color. If we did that parent chain, we only have 1 substituent, and it's a more complicated one. So we want to choose the one with a simpler substituents. So the first parent chain I found with that is highlighted in green with just 1 methyl and 1 ethyl is actually simpler. So for that parent chain, I would say hexane is the parent chain in green that we found. Guess either way, hexane is the parent chain, so hopefully you got the point for that. Hexane is our parent chain, and we decided that our parent chain would follow along this path. 1, 2, 3, 4, 5, 6, with more substituents to make it the simpler substituents. So we could either number it that direction or the alternate direction, which is 1, 2, 3, 4, 5, 6. Either of those. Now we'll identify our substituents would either be 2-methyl, 4-ethyl. Nope, 2-ethyl, 2-methyl, 3-ethyl. If we went in the maroon way, it would be, let's see, 1, 2, 3, 4. 4-ethyl, 5-methyl. So the lower priority is better. So that'll be the substituents. So we have 2-methyl, and then we have 3-ethyl, going with the light blue numbering. Okay, so we're going to combine all this in alphabetical order. 3-ethyl comes first, and then 2-methyl comes next, and then hexane. Okay, and now the very last thing is, do we have a chiral center? So hopefully at this point you would have already racked up basically the way the point distribution is hexane is worth 1 point. Each of these with their numbers is worth 1 point. So if you got the right substituent but not the right number, then you got half a point. And then the very last point is for R or S configuration. So based on the way we've drawn it, we only have 1 chiral center. You can look at this 1 chiral center and know that the hydrogens are pointed towards you. So we're gonna have to flip it, and we have to number each of these chains. So over here we have a carbon, and a carbon, all 3 carbons. These 2 carbons have 2 hydrogens and another carbon. But this carbon has 2 carbons and a hydrogen. So this carbon ends up winning its priority number 1. Then if we continue to compare these two, the next one has 3 hydrogens, whereas this carbon has a carbon and 2 hydrogens. So this is priority 2 and then priority 3. So if you connect that all, it's going to the left, so it's S configuration. But the hydrogen is pointed directly towards us, so if we do the inversion of that, it would be R configuration. So overall, this answer would be R, 3-ethyl, 2-methylhexane. So that's a little bit of a trickier one. I was not trying to be tricky. It's just a challenging question. But you do need to be able to think about how to rotate molecules and name them. So that's kind of why I included a question like this. And we had a very similar question to this on a PLTL packet. So hopefully, if you've been going to PLTL, you've seen a question like this, and this one as well. I think we had this one on recitation and PLTLs, but this question, and we had one on the review like that. This question down here is word for word from a PLTL packet. So if you've been going to PLTL, these shouldn't look shocking to you. Okay, so this question is asking, where would the Newman projection on the left be placed on the given graph on the right? And you should thoroughly explain how you know. So in this, I'm looking not just for your right answer, but communication. So if you're going to become, I spelled that totally wrong. If you're going to become a scientist or a doctor, you're going to need to be able to give your opinion and convince people of it. So any pre-health field, whatever you're doing, you're going to be able to need to effectively communicate. And that's why I incorporate that and giving evidence-based processes in your examples, in your test questions, is because I think it's really important for you to be able to not only get the right answer, but express your reasoning behind it and support it with evidence. So that is kind of the idea behind this question. So if you're looking at this Newman projection, you can see that it is staggered. So that is going to be the more stable option. Whereas eclipsed is higher in energy. We drew that earlier. It's where they're sort of laying right on top of each other. So these higher energies are likely going to be from eclipsed positions. You know, as you keep rotating this, it gets eclipsed, and then you rotate it, and it is opposite. So that's what I think these higher energy is going to be from, or from these eclipsed positions. So I'm going to eliminate those from my answers. I also had a lot of people ask me questions about the free response questions. They felt like these were kind of tripping them up. And you'll see as I'm working this, I actually am not writing anything yet. I'm working through the problem first, and then I write my answer at the end. And I recommend you do something similar so you don't get tripped up in the writing. You basically do your thinking first, and then you do your communicating second. So I've eliminated these answer choices. So because that, just as a note to myself, because it's staggered, it's not going to be at the 120, 240, 360, or 0. So then that only leaves these 3 positions. And all these are going to be in the staggered position, but the most stable conformation, that's the lowest energy, is anti, where the biggest groups are opposite one another, right? So in this case, if you have your big groups, you have a big group here, you want the other big group to be here. And we don't have that. We have our big group right next to each other. So because our big group is right next to each other, it can't be the most stable position. So that leaves only 60 and 60 and 300. So you could put it at either of those positions and it would be considered correct. So the 3 points that you get from this, 1 point is from saying that it would be either at the 60 or 300 position. If you say one or the other, you would get half a point on that. The next thing is saying how you know. And so I want you to eliminate, the way I kind of structured it is you get a point for eliminating the higher positions based on them being eclipsed, and then for eliminating the lowest position based on it being anti. And you can write that in your own language. I'm not looking for you to say word for word what I've said, but I'm looking for you to express those ideas in a way that is communicative and clear. So for those, the next thing I would say, I chose this position because the higher energy positions, 0, 120, 240, 360, indicate the least stable, which must be eclipsed. Least stable, conformations, which must be eclipsed positions. You could include another sentence like the Newman shown, something like that. The Newman shown is not eclipsed, so it can't be at those positions. The next sentence, it's hard for me to write this all out, and this is a long video, so I won't write out the next thing, but the next sentence I would write is, the only positions left available would be 60, 300, and 180, and I'm confident it's not 180 because that is the most stable position, which would have the large groups opposite one another, which is not shown in this Newman projection. So therefore, I narrowed it down to 60 and 300. So basically, I'm looking for a sentence in which you identify 60 and 300. If you get one or the other, you get partial credit. Then I'm looking for a sentence which you indicate that the relative higher energy we know goes with the eclipse positions. And then the relative lower energy, the last point would be the relative lower energy must be the staggered, and the very lowest is anti, so it must be 60 or 300. So that is how I would approach that. I think that's all the questions. So let me know, or the TA, if you have any questions, and I hope that helps.